All right, hello everyone, welcome to this video. We are going to have an interesting problem about trying to compute the speed that atoms are going to move around with inside the sun. So if we imagine having the sun here, there's going to be lots of hot gas molecules moving around, each one of them in different directions, some fast, some slow. But we can try to figure out what is going to be the average speed of the molecules in the sun, assuming that we know the temperature of the sun. And the sun has different zones, so we're just going to pick just a representative value here of 6,000 Kelvin. And we want to try to figure out, we want to find what is this average speed that the molecules have. Okay, so in order to do this, we need to make use of a few different concepts. The first is we are going to try to determine what is the average kinetic energy of the molecules in the sun. And we're going to make the assumption that this is an ideal gas. This is a monatomic ideal gas. And I'm not going to go into the motivation for that decision, but if we make that decision, then an equation is available to estimate this average kinetic energy of these monatomic gas molecules will be 3/2 kT. 3/2 is just a numerical factor. K is a number, a variable for the Boltzmann's constant, whose value is 1.38 times 10 to the minus 23 joules per Kelvin. And over here, we're going to have just the temperature. The key thing is that this is absolute temperature. So you have to express it in Kelvin. And we're going to use that as the temperature of the sun. So we can put in our numbers. And now for the temperature. And this will allow us to compute what is going to be the average kinetic energy. The value will be 1.24 times 10 to the negative 19 joules. Okay, so that's an intermediate result. We are still trying to find the average velocity. And now we can just use the definition of kinetic energy. Kinetic energy is equal to 1/2 mv squared. And of course, since we're using average kinetic energy with this little bar over it, then we're going to have average velocity magnitude in there. And so we can now solve for the average velocity or the average speed, and that will be multiply basically both sides by 2, divide by m, and take the square root. So here's what it looks like, just multiplying both sides of the equation by 2 and dividing by m, and then we can take the square root like this. Okay, so we could plug in our kinetic energy, our average kinetic energy in over here, but we still don't have the mass, so we need to do some one more side calculation. And to find that mass, we will start with the molar mass of hydrogen. So the molar mass of hydrogen is going to be equal to 1 gram per mole. And if we want to express that actually just in grams and then eventually in kilograms, we need to convert moles into individual atoms, because as you know, a mole is a very large collection of atoms. So this is 1 gram for this huge, huge collection of atoms. But we can use a conversion factor that 1 mole is equivalent to Avogadro's number, 6.02 times 10 to the 23rd, in this case atoms. So now the moles will cancel out and we'll have essentially grams per atom if we were to divide 1 over the 6.02 times 10 to the 23rd. And let's just put in for good measure here conversion to kilograms. So 1,000 grams is 1 kilogram. Now when we multiply this out, everything cancels and we have kilogram per atom. And that number will come out to be 1.66 times 10 to the negative 27 kilogram. We would expect it to be a very small number, and it is. Okay, so now we have this other intermediate value. We plug everything now into our equation for the average speed. So I'll show you that here. 2 times the average kinetic energy, which is 1.24 times 10 to the negative 19 joules. And now the mass of a single atom, which is 1.66 times 10 to the negative 27 kilograms. So if you put all those numbers in, let's see what we get. You will get approximately 12,222 meters per second, and we can go ahead and write that in scientific notation. It's 1.2 times 10 to the 4th meters per second, which is pretty fast. All right, so there you have it. We have estimated the speed of gas molecules moving around in the sun when they're at a region of the sun that is at 6,000 Kelvin. This is a little bit of an approximation because we use the 3½ kT formula, which may not be strictly true, but it is an approximation, and we are able to get a value, about 12,000 meters per second. All right, well, thanks so much for listening, everyone, and I'll see you in the next video. Bye-bye.